I want to start talking about something called the topological filtration. The idea here is that if X is one of our schemes, it's quasi-projective OK, that's it. Then I had this Grothendieck group G naught X, of course I also had K naught X. This was the Grothendieck group of locally free sheaves. Sorry, of coherent sheaves. So this comes equipped, I claim, with a natural filtration. So I'll define Fp G naught X equals subgroup of G naught X generated by classes F such that the dimension of the support of F is less than or equal to P. Makes sense? So this is an increasing filtration. And it's a finite filtration because our X's are all quasi-projective over a field. Let's also ask ourselves, do we know any natural elements in Fp coming from earlier? So if I have Z in X irreducible of dimension P, then I have the class of the structure sheaf of Z in FPG0X. By linearity, therefore, I have a map from ZPX, the group of algebraic cycles of dimension P, to FPG0X. Just by I've defined it on the generators, it's a free abelian group. Now let me pass to the quotient. And once I write it like this, you can guess what's coming next. I claim there's actually a factorization like this. So there is a map from chow P to the graded. Let me try to hand wave through a justification for this, or maybe it's not so hand wave. Let's see. So to prove that it descends to rational equivalence, I have to take the basic rational equivalences, that is an irreducible of dimension P plus 1. So to do that, I'd like to take W irreducible of dimension P plus 1. And I'd like to take F and K W star. And I'd like to understand something about the divisor of F and W. Right? And what is the cycle associated to that, and see that it's 0 in the quotient, Fp mod Fp. So may assume W equal to X, which all also run. Because W sitting inside X, G0 W maps to G0 X, and whatever this relation is already there in the G W. I would hope to have it in the G0 W level, and therefore I'll get it in the G0 X level. I perhaps could have said, and maybe I should, let me just do it here since the notes I tried to write it in the correct order better. This association, therefore I have grade dot F, I suppose. Is that the notation? Grade, sorry, the dot F, because this F is increasing. So I can look at the association X to this graded abelian group. And I claim, for obvious reasons, this gives me a functor from schemes of our appropriate type plus proper maps to graded abelian group, the covariant functor, which somehow corresponds to, it's induced, if you like, if I have f x to y, then I have f lower shriek g0x to g0y, and this preserves the filtrations. Right? So, and then there's a g0x to g0 is just that f lower shriek which I defined in terms of higher direct images of cohomology, etc., etc. And one sees easily that preserves the filtration. So there is a certain functoriality. So in particular, if W is sitting inside X, the invariance for W mapped to the invariance for X, and my rational equivalence, basic one, comes from W itself. So I might as well assume W equal to X. And what I'm attempting to do, in other words, is understand something like the class group of X, which is codimension 1 subvarieties of X, mod linear equivalence of Weyl divisors. I'm trying to construct a map to f d minus 1 g0x mod fd minus 2 g0x. I want to get a well-defined map here coming from divisors. Of course, this is sitting inside just g0x mod fd minus 2 g0x. So my problem is to show there's a well-defined map like this. In other words, if I just wrote div x for Weyl divisor on x, this is a quotient. What I constructed just by definition was a map like this, and I want to argue with factors. So this is our problem. Does there exist a factorization like that? Now I can do some fiddling around here. I can replace x by its normalization. Nothing wrong with that. X is an integral scheme, quasi-projective. It certainly has a normalization, it has good properties. And that's also a proper map. And the way the divisor of function is defined on a general integral scheme, go to the normalization, take the divisor of the function there and push it down. That's one of the compatible properties. So rather than just saying this thing came from W, I can think of it as coming from, so to speak, the normalization of W. So if I call this map whatever h, then I can look at h lower shriek from g0 x tilde mod fd minus 2. The dimension, of course, is the same, but I may change the dimension from p to d. Sorry. Let me not try to fix that now standing here. Right? So the rational equivalence already lives here. So if I can check that there's a map here, then I'll be fine, at least for the classes in question there, right? In fact, I guess it is the case that class x tilde to class x would be surjective if the ground field K is algebraically closed. And if not, I'll leave you to think how to get around that. But in case the rational equivalence, the element which I wanted to show goes to 0, the specific one, that certainly comes from this side. So if I check there it's 0, I'm done. So now, therefore, may assume x is normal. Okay? I'm just giving you a kind of argument. I'm not saying this is the only way to do it. There are lots of ways, but I'm just going through some argument using all the facts which I have at hand to do it in some ad hoc fashion. So now let's look at the singular locus of x. Has codimension at least 2, has dimension at most d minus 2. So now I can look at the natural map from g0x to g0 of x minus its singular locus, and I've changed x only in codimension 2. So if I divide by f d minus 2 is clearly the same. We have divided by all things of dimension at most d minus 2. So there is no loss of generality in assuming x is non-single. So now I've got f in kx star, and I have divisor of f is f. Let me write it as d0 minus d infinity, where d0 equals zeros and d infinity is the poles. And I'd like to know whether the class of d0, so to speak, the class of O d0 that's my problem. But notice that I have exact sequences 0 to OX of minus d0 to OX to O of d0 to 0, 0 to OX of minus d infinity to OX O d infinity to 0, right? d0, d infinity are effective divisors. These are, well, apparently the ideal sheaves, but in fact they are now invertible sheaves and they are isomorphic. Therefore, the class of O d0 is equal to the class of OX minus the class of OX of minus d0, which is of course the same as the class of OX minus the class of OX of minus d infinity, which is equal to class of O d infinity. Okay? So ultimately, I brought the connection back between divisors and line bundles and argued saying two divisors equivalent is saying the line bundles are the same, or right on. Perhaps if you want to be very careful, it's a question of what is the definition of the Grothendieck group. I took the definition as, what did I actually write? Did I write isomorphism class or did I just take the free abelian group? Yeah, in any case, the point being two isomorphic things do have the same class even if you took the definition as just take all covariant sheaves, take the free abelian group on them and then divide by equivalence. Because, exactly, take the isomorphism, that gives me an exact sequence, isomorphism to A to B, A isomorphic to B, co-kernel is 0. So therefore class of A is automatically equal to class of B. Provided I know the class of 0 is 0. That I'll leave you to figure out why the class of 0 is automatically 0. Anyway, okay. What is the notion of an exact sequence? Exactly. Right. Okay. Very good. And what do we have? Many 0 objects which are all each individually canonically isomorphic. You have to do something more. Okay, right. It's one of the horrible things. If you look at the definition of higher algebraic K theory, it uses all the objects in the category, so to speak, whatever that means. So, and it builds a simplicial complex out of them. So you have many zeros, each one gave me a vertex. The isomorphism between any two zeros give me an edge. Given 3 zeros, you have a triangle in the space. The point is this whole huge, possibly infinite dimensional object is contractible. So it doesn't. Well, whatever. Sorry, yeah. Yes. Because xing is codimension 2. So it makes no difference. I've thrown away only a codimension 2 set and I've divided by the class of all sheaves of codimension 2 or more. So in the quotient it doesn't matter. See, it's not that it's important to write the argument like this so much. I'm giving you a style of reasoning for things of this kind. If you need to work with these functors, here's some abstract definition. All you got is some functorial properties and in a few cases you have some concrete things. How do you squeeze it and get juice out of it? That's somehow the point. So you have to do tricks like this. Okay, I didn't bother to write a proof. I just said it's obvious in the notes. Huh? But then I thought, no, maybe it's not. It requires some thought. I mean, you can always look it up in the book. Right. So we found a relation, therefore, between the Chow groups and these graded things. So there's this functor, x goes to grade f g0. It is a covariant factorial for graded things, but in fact, I mean, so to speak, x could go to Chow star x, and then it could go to this theory, grade f dot g0. Right? These are two such functors, and what I've managed to do is I've managed to construct a natural transformation. This is a natural transformation of functors. Okay? So what I'm saying is that, of course, I have this for given x. If I have another y and a map to x, or whatever, I have a map x to y, which is proper, I can apply f lower shriek on this side, and I can apply f lower star on this side, and the diagram will come out. Right? That's what it's saying. So I've constructed some sort of quotient of the Chow group functor purely using sheaves. Now let me assume x is non-singular. Then I know that k0x is isomorphic to g0x. So there exists topological filtration also on k0x, because it's isomorphic to g0, so I can pull the filtration back under that. Now, on k0, well, here this is a relation between the Chow groups of x and grade p g0, which in the non-singular case, so in other words, here I therefore have Chow p x to fp k0 x mod fp minus 1 k0 x. This is surjective. But on the other hand, I also have some relation between k0x and Chow px. Let's say is rational coefficient. Yeah. I forgot to say it's surjective. You are completely correct. That's very important. Yeah. I just asserted surjective here in passing, and I should have pointed out that it is true. It follows. Surjectivity also, there are different ways you can do it. One way is to do this kind of trick. To delete something of lower dimension, it doesn't change the quotient, but it makes any sheaf into a vector model, if you like, or appropriately. Yeah. Okay? Making sense? If I have a sheaf, or in other words, let's put it like this. Suppose I have a sheaf f and support of f. Suppose support of f is v, and for simplicity, let's assume it's irreducible. Then right. So there is v minus v naught, a proper subvariety. Suppose support f is v is irreducible, is integral. Or do I even want to bother with integral? No, just yeah, okay, this is fine. Support v is integral. Then if I have an f, if I have such an f, then I have the ideal of v. Right? So saying support of f equal to v means that IV to the n f equals 0 for some n. It certainly implies this. So now I can replace f in the G0 by direct sum iv to the m f mod iv to the m plus 1 f. So in G0, f is the same as the sum of these things, because you have finite filtration, exactly the growth and deconstruction splits off all those short exact sequences which you would get in that fashion and replaces the object by the sum of the graded pieces. So if I was looking at sheaves f which support V, I can think of V as actually the scheme theoretic support of the sheaf, or at least the scheme theoretic support is contained in V, if I want. These graded pieces, one of them, all I'll know is that the support is contained in V, okay, in general, because ideal theory could be very complicated. F could be some horrible thing, right? Some whatever. Even if F corresponded to O mod an ideal, that ideal could have had a primary decomposition and embedded primes and all sorts of nasty things could have happened in principle. But when I take such a graded thing and look at all those nasty phenomena, whatever they are on proper subvarieties of V. V, so to speak, comes from a minimal prime, which is giving the dimension of the support. So all such complicated algebraic phenomena happen in lower codimension. So modulo the next level of the filtration of G0, I can just neglect all those bad things completely. Just remove them. It doesn't change the result. Right? So I'm just left with basically the situation where F is like a locally free sheaf on V, but in fact I can even make it free by again deleting a subvariety inside V. So F is like the trivial bundle on V. So it's the class of V so many times. Okay? I hope you understand. Up to replacing F by some graded, and then up to modifying in lower dimensions, I can make F essentially OV. F it becomes equivalent instead to OV to the M, to the R, or some R. That's the class of this OV to the R is just R times the class of OV. So it is one of the elements in the image of the cycle group. This is the reason for surjectivity. Right, there are some details to check. I'm not saying it's completely obvious, but it's not super hard. Okay? Right, that's the surjectivity, which I forgot. It's important, I forgot to say it carefully. I just wrote it. Right, so, but I want to make the point that there's also a map in the other direction, which is you take the Chern character on X and take its dimension P part. I mean, the Chern character lands in some graded thing, so there are different parts, one of it is the part in degree P. So in particular, that gives me a map from Fp K0x to Chow P X with rational coefficients. Take the same Chern character, take the dimension P part and restrict it. And so as we just remarked there, mod Fp minus 1, if I want to look at Fp minus 1 K0x, mod this, generators were given by things of the form OV, where V in X irreducible of dimension P. Correct? I mean, that's what I've been using there, up to some lower dimensional errors. And up to lower dimensional error, I can also assume V is non-singular. X is non-singular, is what I assumed in any case. The singular locus of V is a proper subvariety, that's lower dimensional, I'll remove it. So, up to modifying in lower dimensions, we can assume, so V non-singular, up to lower dimension modifications. Then the inclusion of V in X is a regular embedding of a certain fixed codimension. that implies the churn character of OV looks like the class of V plus lower dimensions, because there will be a Todd class and so on. And V is a regular embedding. That's right. I have the Todd class as a normal bundle. Todd class of anything is 1 plus higher degree terms, and I write it in terms of chow upper I. So in terms of chow lower I, that means it's 1 plus lower degree terms, so to speak. Lower dimensional terms. Higher codimension, lower dimension. Right? So the other terms have lower dimension. What that will tell me is that this implies this map I was attempting to write from here to here used, so in particular I restricted here, I was looking at churn x in dimension p. I got a map like this. And certain specific elements here, I said this went to the class of V here. That's what this is saying. Huh? I mean, the calculation, I removed some small sub-variety not to do the calculation, but if I put it back, it doesn't change the chow group. Because whatever modification I did is in dimension smaller than the dimension of V. That's in other words, dimension smaller than P. That doesn't, if I take X and X minus something of dimension less than P, it doesn't change the P chow group. Right? So if that equation held after deleting some small set, it holds without deleting anything. So the upshot of all this is that I have chow Px goes to Fp K0x mod Fp minus 1 K0x. And by the same token, whatever I argued here that Fp sits inside chow P, that means that this is the full churn character. Huh? I didn't truncate it anywhere. This is the entire churn character. It means that the churn character of OV starts with V and lower dimensional chow groups. So if I take something already of lower dimension, it doesn't contribute at all in dimension P. The contribution from Fp minus 1 from the churn character would have been in chow P minus 1 and lower. So the chow P part, this goes to 0. Okay? With the same reasoning. Put a different way, K0 comes with a filtration, the chow ring comes with writing it in terms of dimension, it has a dimension filtration on that side also. I am arguing here the filtrations are compatible, so the gradient must be compatible. So what that gives me is that the map here, of course here I am supposed to put Q coefficients because I use the churn character. Right? Riemann-Roch was for the churn character with Q there. But this has the property that if I took a generator V here, it went to the class of OV mod Fp minus 1, and then it again went to the class of OV, but now concerned with rational coefficients. Class of V, sorry. Now tensor everything with Q. Then that's just, the map from here to here is just a natural map from the chow group to the chow group tensor Q, because that's what it is on the generator. So tensoring with Q, I find that chow Px Q, and remember we argued that this map is surjective. I gave some kind of hand waving reasoning. Grade Fp this is still surjective, and this is the identity. Therefore, both maps must be inverse isomorphisms. So in other words, if I am looking at the rational chow groups, this is saying, at least after having proved the Riemann-Roch theorem, I actually didn't need them at all. I already had it at the level of K0. K0 is there. K0 is the same as G0 with sheaves. Then there's a filtration by codimensional support. Take the gradient. I never need to refer to cycle at all. I could have worked entirely with sheaves and bundle. Except that in the argument here I used this.
So rational equivalence replaced by exact.
Exactly. Precisely. And in a sense, you can see this is sort of the connection. I mean, this was the connection. Okay, now let's go on from there. All right, suppose I found this out. Now, various things might immediately occur. For example, I can ask, I have K0x, and then here I have chow star x cube. Write it up or down as you like. Now I'll write it with codimension. It's the same filtration re-indexed, and I put q here if I like, and then here I had churn x, and I know this is an isomorphism, but this side doesn't have a grading in a natural, obvious way to me. What I have is only a filtration. I'm saying, okay, let's put it like this. This comes with a filtration. There's a churn character. I just asserted it's isomorphism. This also requires proof. Why is it isomorphism without the grading? Well, that's because I have a map from a filtered thing to a filtered thing. Passing to the associated gradient, it's an isomorphism. And the filtrations are finite, therefore it's an isomorphism. The original map, which may not, I mean, which didn't make sense to talk about it being graded, it's only filtered. Okay. Am I making sense? I've argued here that this churn character thing preserves the filtration. If I think of the filtration on the chow group using the dimension. Of course, chow group has grading, it's better than filtration. But this side I had filtration and the map was compatible. That's what we argued there. And on the graded pieces, it is an isomorphism by the reasoning I gave there. Therefore, the map without taking graded is also an isomorphism. But now the without graded means this side is possible to split into direct sum. It must be possible naturally to split into direct sum that side. Just like I said, I managed after Riemann-Roch to actually remove the chow ring entirely by just taking the graded Q coefficient. What is the splitting, but that used the graded in some fashion, used dimension or whatever. There's some intrinsic way of understanding the filtration. That's one of the many types of things which might occur in this context. So let's try to get in that direction a bit. So the answer is, for example, if we ask what is the induced grading on K naught. So the answer, answer involves what are called Adams operations which in turn come from lambda rings. And Grothendieck's so-called gamma operations and gamma filtration. So I'll try to explain what these things are. I could just do everything directly in terms of bundles, but I thought a little bit I should say something about this abstract thing called lambda ring, because it's got, of course one can go on, there's even a whole book of Fulton and Lang, which I've given a reference to. Couple tells me there are mistakes further on in the book. You go, it's broadly correct, but it's a bit sloppy. In any case, the point of view is quite interesting. So you define some algebraic structure called lambda ring. So lambda ring with positive structure. One might also write lambda ring, Greek lambda there, lowercase Greek lambda, consists of 1, a commutative ring K with 1, to a sequence of maps lambda I, that's why it's lambda ring, k to k, I greater than or equal to 0, such that various conditions are satisfied. Lambda 0 of any x is 1, lambda 1 of x is always equal to x, and such that the map lambda t, the lambda series so to speak, from k to k power series t invertible elements given by lambda t of x is some lambda I x t raised to I. Lambda 0 is 1, so it's 1 plus tx plus higher degree terms, whatever it is. So it's certainly a power series, is a group homomorphism, is an additive homomorphism. This just means basically that i.e. lambda n of x plus y is just sum I equals 0 to n lambda I x lambda n minus I y. And this is writing this for each n is the same as saying this is a group homomorphism. This is just the lambda. I have to tell you what positive structure is. I'm getting that. Third, there exists surjective ring homomorphism epsilon from k to z is called augmentation. And 4, there exists a set E contained in k minus 0 called positive elements such that E union 0 is closed, is an additive semigroup E generates K as an additive group, that is E minus E equals K. E dot E is contained in E, so E is also closed until the multiplication. And 5, epsilon of E is contained in the natural numbers contained in Z, the strictly positive integers. Further, if E in capital E, epsilon E equals R, which is of course greater than or equal to 1, then lambda I E equals 0 for I less than R, and lambda R E in K cross is a unit. Yes. Correct. And all this is some abstract way of writing down the properties we know of vector bundles. If you take lambda I to be the ith exterior power, So basic example, K equals K0x, E equals the set of all classes script E such that script E of vector bundle not equal to 0, of course. Epsilon equals rank, and lambda I equals lambda I of the class of E is the class of exterior I of E. Okay. So there is this operation of exterior powers for vector bundles, and it does have vector bundles do have a rank. It's a positive number. A class in K0 is the difference of class of two vector bundles. If the rank of a vector bundle is R and I take its rth exterior power, that's a line bundle. So I'll define things called line elements. Is E intersection epsilon inverse 1, so to speak. It's the elements of E of rank 1, of whose augmentation equal to 1. So then, according to the axioms, 1 is the highest non-zero exterior, and lambda 1 is itself. So the element is itself invertible. So all these properties are certainly true for vector bundles and things. And exterior, why does it descend to the Grothendieck group? That's the only comment one needs to make. That's just saying if you have a short exact sequence of vector bundles, there is a relation between the exteriors of the two terms and the exteriors of the middle. So the statement is this: if you have E prime to E double prime to 0, then exterior RE is filtered, if you like, by images of exterior S E prime wedge exterior R minus SE image of this. Well, okay, tensor even. Such that the grade is the grade E prime directs from the grade tensor. So, yeah. Directs from I equals 0 to R exterior I E prime R minus I E double prime. This is correct. And these are some standard exercises in hard. So of course you may ask, why bother? I've already got vector bundle, I already know all these properties, why write down this long elaborate definition? Well, there's a point that I can continue the abstraction a little more. I can consider lambda rings, then there's some further things called special lambda rings. So what are they? I'm just indicating things, I'm not really checking lots of stuff. So the point is, there are identities lambda I of x dot y is pi of lambda 1 x lambda I x lambda 1 y lambda I y, where there are certain universal polynomials pi of T1 Pi S1 Si in I guess in this case Z there are certain universal polynomials Pi in these variables, so that if you substitute the classes of E and F, two vector bundles, the ith exterior of E tensor F is this in the growth group, meaning it has some filtration was graded, is that particular polynomial in the exterior of the two individual vector bundles. I'm not going to say what this formula, there is a formula, right? And there's some universal formula like this, but it's much more complicated. Nobody wants to write this down explicitly. It is there, it exists. And similarly, there's another formula, another such one of those universal things which gives me lambda j of lambda k of x. This is supposed to be p j k of lambda 1 x, lambda j k x. So we want to compose two exterior power operations and then think of filtering that object suitably and going to the graded. It will be expressible in some fashion in terms of this many exterior of the original guy. In general, this business of taking these simple looking representation functors and composing two of them and understanding what happens to the result is a very, very nasty problem. It's essentially, in full generality, unsolved, I would say, in most cases. When you take some representation of GLN into some vector space or some dimension D, then another representation of GLD in some other vector space, compose them and ask me what is the decomposition into highest weights and things. We don't know, basically. And there is there's some theory, there's some formalism you can do, but we don't have an answer you can just write down. Yeah.
This is what is called
Platism, exactly. So this is an example where we compose two such natural looking functors and you get some, we know there is a result. In any I equal to 1, j equal to 2, something, you'll be able to work it out easily. In general, there is something and it will have some formula, whatever. So there are some identities. So special lambda ring is where you got the ring and the same identities, whichever are underlying vector bundle, are true in this abstract ring. Okay. Great. So why bother with all this stuff? I can now also make sense of an extension of lambda rings. Sorry? Well, these identities are, I just said it, I didn't write it down. Yeah. There are these identities for composition and identities for the multiplication, which are true for actual exterior vector bundle or vector spaces, whatever they are. So, just abstractly ask for the same identities to be true. It is remarked that if you take the group of units, take the multiplicative group and think of that as addition, and think of this formula as giving multiplication, and this formula as giving exterior. This multiplicative group acquires a lambda ring structure, and this is a morphism of lambda rings. That's what this is supposed to be. Okay. It doesn't matter. Growth theory set up all this stuff. So why bother with this? I'll come to it in a bit. There's some point. Extension of lambda ring. So here I've got a lambda ring. So this is an over ring K prime containing K such that lambda I K prime restricted to K is lambda I of K. Now it extends the lambda operations, and there exists epsilon prime E prime satisfying similar conditions. I mean, it's fairly obvious what the condition ought to be. So, what one is going to be interested in is a class of lambda rings which satisfy what's called the splitting property. This would say if I have a lambda ring K and I have an element X in K, or even let's say E in K, E, a positive element, let's say, then there exists K in K prime extension, and line elements, here suppose epsilon E equals R, which is so to speak rank R, and line elements alpha 1, alpha R in L prime contained in E prime contained in K prime, such that X equals alpha 1 plus alpha r. Right? This is also something, abstracting something which we have at the level of vector bundles, the so-called splitting principle. I write everything as a sum of line bundles in some bigger Grothendieck group. Then the claim is that lambda t of this element E is in fact product I equals 1 to r 1 plus alpha I t in k prime power series t cross. Right? So if your particular element E happen to split in some extension, I can write formula for the lambda I. So lambda I E is ith elementary symmetric polynomial in these line elements alpha 1, alpha r. And sort of in the end, the point of all this game is that there is an abstract algebraic lemma, which is the following. Let capital K be a special lambda ring. There exists unique lambda structure on what I'll call K. Let this be a lambda ring, and E in E, let's say epsilon E equals R. Sorry, let me give myself a positive element. Then there exists a unique lambda structure on something which I'll call KE equals K bracket T mod PET, which of course contains K. PET is the following polynomial. So I claim, given an element literally, I'll construct in some explicit fashion an over ring Ke. Because this is a monic polynomial, this is injective, right? And this identity is going to be satisfied. So if this satisfies, if L equals image T, so the capital T of course produces maps to something in the quotient, the root so to speak of that equation. Then E prime EE, the one in the new Ke, is the semigroup spanned by the original E and then this new L and E minus L. So suddenly E minus L in this new ring, first of all L is a new line element which I constructed in the ring, and E minus L is positive with the new thing with epsilon 1 less. So in some formal fashion I split off a line bundle, class or line bundle from the class of this E, so to speak. This is nothing to do with algebraic geometry or splitting of projective bundles or anything. It's like adjoining a root of a polynomial in an abstract way. That's Grothendieck's observation. That really, once you accept that they have vector bundle and they have exterior powers and they have some formalism, intrinsically algebra produces some over ring where I can formally define exteriors, I can formally define everything and split the class of E.
Like the spectrum.
Kind of, yeah. I would think of it as like adjoining a root of a polynomial. I mean, it's like that. So, I just want to, I don't want to go further in this direction and I'm not going to prove it. you can imagine it's some sort of mess of algebra to do it. But at a conceptual level, it's interesting. It says that I didn't need to understand geometry that pull back a vector bundle to some other space and split line bundle. That's not required. The moment I accepted exterior powers and their formalism, automatically it will be possible to split in some formal way somewhere else, which is constructed in an abstract algebraic way. And then in that place you can construct Chern classes, you can construct everything, you can formulate the entire Grothendieck-Riemann-Roch somehow in that abstract language. And that's this so-called Riemann-Roch algebra, as they call it. Of course, exterior powers are there at the level of geometry, but what is being said is intrinsically that's all you need. That and some abstract algebra are all you need. You don't need these other spaces and auxiliary, whatever things. Fine. So now let me just go back to the thing which is really what the reason I just brought this up to point out there is this abstract thing at the back, which is constructed by Grothendieck, and maybe it's of interest to look at it. That exterior powers are really what are responsible for many things. Now let's get to the specific stuff about the grading, Adams operations and gamma filtration and the like. So suppose K, you can set up Adams operations with this formalism. So let K be a special lambda ring. Lambda T, K to K power series T cross x goes to some lambda I x T raised to I. And now you can do operations on the other side. So I can define psi Tx to be epsilon x minus T d by dt log of lambda minus Tx. You can do it. You can write this down. So this is some I greater than or equal to 0 psi I x T raised to I for some new operation psi I, which are some function of the lambda with rational coefficients, I guess, because you wrote a log. Now d log is anyway would be differentiate term by term and divide by the same thing, right? That's correct. And then I multiply by t again. So that also does something. And then multiply. Exactly. That's right. Okay. Let me write proposition. What are the properties of these things? Why are they better? So let L contained in K be the line elements. One, if U in L, psi j U, I wrote it psi lower I, it's psi upper I. The reason is it's somehow contravariant is the way you should be thinking. Anyway, it's just notation, but I'm writing, I want to think of it like lambda I, lambda upper I. That's how, for whatever reason we think of it, yeah. Right, psi j of U is just U to the j. On the line elements, this new operation is just raising to the jth power. Exterior operations, by the way, are trivial, right, on line elements. Lambda 1 is the element, lambda I is 0. So this is kind of certainly a new operation. 2, psi j k to k is a ring homomorphism. Lambda didn't interact so well with the ring structure. Additively, okay, I got something. Multiplicative, I had to write this abstract thing and I couldn't tell you what it is, say they exist universal polynomial. I couldn't write anything down. It was too unpleasant. This other is a ring homomorphism, psi j. Each individual psi j is a ring homomorphism. Third, psi j or psi k of x is equal to psi k or psi j of x. They commute. I guess the lambdas do not commute. Right, there's some horrible form. For lambda could have been symmetric, but it's not. I should think about it. Right? So all these properties I claim are pretty easy. Well, let me first check it for line elements. So lambda minus t of u is 1 minus ut, right? If u is a line element. Lambda sub t of u would have been 1 plus ut, but I made minus t, so it's 1 minus ut. Epsilon is 1, so t d by dt log lambda minus t of u turns out to be just ut or 1 minus ut. This sum j greater than or equal to 1, u to the j, t to the j. And then I added the epsilon there, so I got the 0th power of the 1. Yeah. Okay? Psi 0 is 1. And then for general elements, use splitting lemma for special lambda rings. And if you don't like special lambda rings, if you didn't digest the property, of course, in the example at hand for vector bundle, we do know splitting. Okay? I mean, then I claim I'm not doing the calculation, it's not difficult. Once you know it for line elements, anything is a sum of line elements, it's easy to prove. I mean, lambda t of a sum is product of the lambda t's. So log of lambda t of the sum is the sum of the logs. Therefore, it becomes additive, and so on. So these psi j's are called the Adams operations. They're kind of important. Then there's also other operations introduced by Grothendieck, the gamma operations. I need them also. So here what you do, so these are a sequence of maps gamma I, k to k. So again, k special lambda with the positive structure. So I want to get maps gamma I, and the gamma series is lambda of t upon 1 minus t of x. Right? So put a different way, sum over I, lambda I x, t upon 1 minus t to the I is summation gamma I x t to the I. So each gamma is some combination of lambdas, smaller lambdas. And then let's work out a couple of identities. I should remark the following, then one makes the following remark. If you map k power series s to k power series t, where s goes to t upon 1 minus t, this gives a ring isomorphism. It's a change of variable. So if I know that I have the lambda identities with values here and compose with the isomorphism, I'll get the same formal identities there as well. So I'll get the following property, that gamma k, therefore gamma I define a new lambda ring structure on K. And it also defines a new special lambda ring structure. That's not so obvious just by saying change of variables, But if I say that the notion of a special lambda ring comes from some universal way of putting a lambda ring structure on K power series T cross, with this multiplication of power series being the addition and some other operation of multiplication and lambda, and then say the original thing is a map of lambda rings, then choosing an isomorphism of K power series T with K power series S, I can transport whatever the abstract structure is and I'll get it on the other side. So the special thing will also automatically be satisfied. If you really try to verify it by hand with identities, you will be in serious trouble, I think. In any case, it's good to see abstractly that it's going to be right. That means I can write whatever identities I had with lambda, I can rewrite it with gamma and they'll be correct. So now let's use this to do some computations. Let's take U in L, a line element, and let's look at lambda T of U minus 1 and do a computation. This is lambda T of U divided by lambda T of 1. Right, remember, lambda sent addition to multiplication, so it sends subtraction to division. So this is, if you think about it, 1 plus ut over 1 plus t, right? That's the definition. So then I get gamma t of u minus 1 is here, I'll just substitute. So it's 1 plus u into t over 1 minus t over 1 plus t over 1 minus t. In fact, this is why you want this substitution, because this is just 1. So this becomes 1 plus u minus 1 times t. This is the definition. Gamma t is this. I mean, yeah, times 1 minus t. Of course. Multiply numerator and denominator of 1 minus t is the way to do it. Yeah. No, it's not 1, but after simplifying, you get 1 there. That's the point. So, in any case, this is correct. So, therefore, that computes that gamma 1 of u minus 1 is equal to u minus 1. Gamma I of u minus 1 is 0 for I greater than 1. Okay. Now, let me instead compute gamma t of 1 minus u. I'm doing all these silly computations, but in the end, I'll use them to define another filtration, the so-called Grothendieck gamma filtration. That's the point. I'm getting to it. And I want to get some properties of that filtration that will depend on these identities. Yeah.
The point is that U is the line element.
Yeah.
Say for the divisor. U minus 1 is the class of OD minus 1, which kind of represents the class of OD.
No, it's the class of normal bundle of D. 1 minus u is better.
1 minus u.
Or 1 minus u inverse.
1 minus u inverse
Is the structure sheaf of D.
No, I'm just saying therefore.
Yeah, it's going to come in the, I mean, I'm good. When I try to explain some things about the gamma filtration, at that point if I've forgotten to say, please interject, because that's some of the point. Let me compute gamma t of 1 minus u. It looks like I'm fiddling around here. This is 1 over gamma t of u minus 1. Again, gamma t being supposedly a lambda structure, minus is division. So, changing u minus, it gives me this, and I had a formula there. This is 1 upon 1 minus u t, which is sum I greater than or equal to 0, 1 minus u to the I, t to the I. So, gamma I of 1 minus u is 1 minus u to the power I. That's what I deduce. So, now let me try to define the gamma filtration. Remember, the topological filtration that I used earlier said K0 is isomorphic to G0 in the non-singular case, and therefore I got a filtration by dimension. But here I have only used vector bundles and exterior operations, like they work for any x. There's no non-singularity involved. Okay, so that's one aspect of gamma of this pointer. So let's define. So on k0x I'm saying, but I can actually as well make sense on any special lambda ring K. So let's define F1 gamma of K to be just the kernel of epsilon. So in the bundle case, this will be the virtual bundle of rank 0. I just take F1 as that. For n greater than or equal to 2, let Fn gamma of K equals abelian group generated by all monomials gamma R1 x1 gamma Rk xk with x1 xk belongs to F1 gamma and R1 plus Rk, the sum of the exponents is at least n. It's some kind of monomial of degree n in these gamma. Okay. Now let's compute that if x and xk, x and k, and I compute the product take one of these generators and multiply it by x. I'll write that as x minus epsilon x times the same thing sorry, this is not gamma I, it's supposed to be Ri. Ri is okay in the notes. When I try to write on the board, R and gamma look the same. I'm sorry. Plus epsilon x, which is of course an integer, times this. So this element lies in F1. This is gamma 1 of x minus epsilon x, I guess. No, whatever it is. It lies in F1. Yeah, it's equal to gamma 1. Gamma dot was a lambda structure. A lambda structure had the property that lambda 1, the first operation, is always the identity. The 0th operation is 1, the first operation is identity, higher operations are whatever they are, right? So the point is, I've written this as a sum of two terms. This is a product of this is a monomial of even higher degree, and this is an integer multiple of the same monomial. So the Fn, so it says that k times f n gamma of k is contained in Fn gamma of k is an ideal. The Fn gamma is an ideal in the ring. Okay, and it's a filtration. Fn gamma k multiplied by Fm gamma k is clearly contained in Fm plus n gamma k. So I've got a filtration of the ring by ideals. So I can pass to the associated graded ring. I can talk about grade dot gamma of k as direct sum n greater than or equal to 0 Fn gamma of k mod Fn plus 1 gamma of k. You can make sense of this already. Now, therefore, if I have an E in E, I can associate to it C upper I E, which is defined to be gamma I of E minus epsilon E. And this, by construction, lies in Fi gamma k mod Fi plus 1 gamma k. I call this the Grothendieck Chern class. Sorry? E is a positive element, E in capital E. So let's get some sense of what this might be. Suppose if epsilon E equals M and E equals U1 plus UM, where UI a line element, suppose my element happens to split, then can I compute this thing? Then let me try to do some computation. Let's notice that CTE, the so-called total Grothendieck Chern class, which is by definition summation C upper I E T raised to I, is just, I claim, product I equals 1 to M, 1 plus AIT, where, what is AI? AI is equal to C1 of UI, which is UI minus 1 mod F2 gamma. Okay. That's just saying I can try to compute CI. Right. I'm just using the gamma identity. Remember earlier I said if I had a lambda ring and my element x is a sum of line elements, then I can compute the lambda I as the elementary symmetric function of the entries. Now I've changed the lambda ring structure to this gamma, but still the abstract thing that it is given by the elementary symmetric functions, but of the gamma 1s of the invertible elements. That formula is correct. Okay. Now the key proposition is the following, which is some of the interest of the whole game. For j greater than or equal to 1, n greater than or equal to 0, if x is in Fn gamma k, then let's look at the jth Adams operation on this x. I claim this is just j to the power n times x mod Fn plus 1 gamma k. So Adams operation was defined in some complicated fashion involving lambdas, and gamma is again defined in some fashion, and I have the associated gradient, etc. But if I look at the gamma filtration and look at the graded pieces, the Adams operation acts on those graded pieces, so to speak, and it acts as a scalar on each graded piece. The jth Adams operation is just multiplication by j to the n on the nth graded piece. Right? Even though lambda was something rather complicated, when you rewrote it in terms of Adams and took into account this filtration, the operation has suddenly got fantastically simplified. So let's try to check this if we can, at least get some idea why it's right. So suppose x is equal to, is the product I equals 1 to n ui minus 1 ui in L, then let me make a computation. Psi jx is product I equal 1 to n ui to the j minus 1, because psi j is a ring homomorphism. So psi j of x is the product of the psi j of those things, and those things, I know how to do it for line elements. But I claim this is just product I equals 1 to n ui minus 1 times product I equals 1 to n 1 plus ui to the n minus 1 j minus 1 j minus 1. So I took the jth power, of course I get j minus 1. I claim this is just each of these u I to the r to the s is congruent to 1 mod f1 gamma k. It's a line element. If ui is a line element, any power is a line element, right? That's, yeah, I should have said epsilon was an augmentation. Epsilon, I did say epsilon is a ring homomorphism from k to the integers. Then of course on e it's positive and then it multiplies. So yeah. So if each of these things is a line element, each of them is congruent to 1, and therefore this whole expression is congruent to, each of these terms is congruent to j. So this is congruent to j raised to I, j raised to n times x. So if x is of this special form, this is correct. Then you are supposed to be able to reduce the general case to this. Let me not splitting. Okay. So of course, once I've simplified these operations in that fashion, then I can get a conclusion. Suppose fd plus 1 of gamma kq is equal to 0, some d. So let Vjm be contained in K. Fd plus 1 gamma of Kq. I'm assuming some boundedness property. Yeah. The filtration is bounded on the lambda. Yeah. You need some nilpotent. Yeah. Yeah. Otherwise, you have to do other kind of assumptions that every element is a finite lambda exponent, something of that kind. You have to put some hypothesis. Anyway, let me just do this. Yeah. Let Vjm be the j to the m eigenspace of psi j. Then the theorem is Vm is Vjm is independent of j greater than or equal to 2. That I in fact have a subspace just Vm, which is the j to the eigenspace for each of the individual psi j's, provided j is greater than or equal to 2. Of course, it's also, it's the appropriate eigenspace of psi 1, because that's the identity. So the eigenvalue is 1. It's not so, that's less interesting information. But this allows me, of course, these eigenvalues are different. If j is at least 2, the powers j raised to m are all different. So that breaks up the space immediately into weight spaces. And in fact, you can just write down. That's correct. Yeah. I'll get such a decomposition. And in fact, you'll find that the identity of V, just from fiddling around, linear algebra, whatever, is summation n equal to 0 to d, product m not equal to n, psi to the j minus j to the m by j to the n minus j to the m. Something like that. You can write some explicit expression like this, and this gives me the decomposition to orthogonal idempotence, and everything works. So now let CH be the map from KQ to dot gamma KQ given by this using defined using the C upper I, the Grothendieck Chern classes, and then I get that this new Chern character is an isomorphism. So this is like our earlier Chern character from KQ to the Chow ring is an isomorphism. So in other words, in the end, if we took the example where K is K0x and X is non-singular, purely using vector bundle and things, I could have manufactured the rational Chow ring, the Chern classes, the whole theory, and proved the Riemann-Roch also in that language. I never needed the Chow groups at all. The Chow ring is of course constructed integrally in the non-singular case, but Chow ring's rational coefficients doesn't require the theory of cycles at all directly. That's what this is. And actually in this whole business, this was some abstract business using exterior powers and the like. There was no non-singularity, there was no regular embedding, there's no normal cone, nothing. It's just algebra. So that gives me a kind of Riemann-Roch formalism of an abstract kind, working with any singularities, any x of some kind. But what is this Chow ring exactly? It's grade gamma or something. So what are elements there? How do I think of them? That's not so obvious part. But in any case, what it does do, for example, it says that if you want to set up a good theory of Chow rings for singular varieties where you have Chow cohomology is your Fulton model, but Fulton's Chow upper I are just the resulting endomorphisms of the Chow lower J's. So to speak, if there's an abstract Chow upper I, it maps to some endomorphism ring. It's not injective in general. The examples where you know it's not compatible with the Grothendieck group of vector bundle, very big in certain places, and the cycles are maybe big somewhere else, but not in the right places. So it's not compatible. There are examples. My thesis I construct. That's, but the easier things also. So what's that? This one. Not really. No, it's just finite Kull dimension. Something like that. There's some question about the, one has to then compare the topological filtration of the gamma filter with the rational coefficient, which you can do. And the topological filtration is certainly bounded because the Kull dimension is bounded. Yeah, any actual variety. Okay, so sorry, I just need to make just some fleeting comment. I wanted to end with the comment that therefore I have a rational Chow ring for singular varieties defined this way, and it's not equal to the Fulton Chow ring. It comes equipped with a homomorphism, a surjective one as it turns out, surjective I believe, and it's not an isomorphism. So if somebody wants to construct an integral Chow cohomology theory, the rational model of it is given to you in K theory. That's the constraint you have to satisfy. You have to be consistent with this. I've been interested in this kind of question for a while, and that's what you have to do. Thank you.